Okay, if there's no questions, then I'll go ahead and restart. So we had right, so let's go back before we went on that tangent. Right, so we have a vector x that we know is S sparse. We take phi x, and we want to recover x from y equals phi x. And what we showed is that as long as the spark of phi is large, we can do this via this L1 L0 recovery. Right, so we can do it by minimizing, right, L0 norm subject to phi z equals y. Okay, this has two problems. One problem is that it's actually very unstable, right? I'm not going to discuss it much, but you can probably kind of imagine that, right? If I now have a little bit of noise, right, in the arguments that I was giving, if instead of y, I measure y with a little bit of noise, now if I have to go check which linear combinations of phi gives me closer to y and so on, this can quickly become problematic. So, right, because the L0 norm is so brittle, right? If I just move my vector a little bit, a zero outside of the support might no longer be a zero, and the L0 norm is now very different. Right, it's very brittle, doesn't feel continuous at all, and so this has certainly stability problems. But it also has computational issues, right? So this is computationally difficult, computationally, hard. Or it's in particular what we call NP hard, right? Solving this problem is difficult, right? Essentially, the way to solve this is if one doesn't know anything, is to just try every possible choice of S columns of phi and see when is it that y is in the span. Right, and do this first maybe for, you can do it for less than S, start from small and go, but this of course is a combinatorial thing, and so it's computationally hard. And so here comes a key idea, right, and this idea shows up in a lot of signal processing, machine learning, data science, so on. The idea of convex relaxation. And the idea here is to replace this very brittle thing that's hard to optimize by something that's much nicer, that's convex. Okay, and so first I'll show you a picture of what you should have in mind, and then we'll prove some theorems. Okay? And so the idea is that we're going to consider something called L1 minimization. Okay, and then I'll draw the picture. Right, so we'll do L1 minimization. Right, so this is also what gives rise to lasso in statistics that I'm sure you'll see, and total variation in imaging and so on. Okay? So the idea is that instead of using the L0 norm, we're going to use something else. Okay, we're going to optimize something that I'm going to call L1. So minimize the L1 norm of Z such that we're going to try and solve a different problem. Okay, this is going to be a key idea. I'm going to put it inside the box just to... Okay, so this is a different problem, but it's going to be good for two reasons, right? So in order for this to be useful, right, so we're going to try to recover X, not by finding the sparsest solution to a linear system, because this seems very difficult, but finding instead this minimum L1 norm solution to a linear system. Okay, and this is the idea behind compressed sensing. Now, in order for this to be useful, I would argue two things need to be satisfied. One, right? Maybe I should say, for this to be useful, we need two things, right? We need one, that L1 is easy to solve. Because if it's not easy to solve, then we might as well just solve L0, right? We also need something else, which is that the solution to L1 is the solution to L0 in many cases, is the same, is the sparse vector we want. In many cases. Right? If we don't have these two properties, then it doesn't make any sense what we're doing. right? But if we have these two properties, then all of a sudden it makes a lot of sense, right? Because now we have a problem that gives us the object that we want, and that is actually easy to solve. We can do it on the computer. Okay, so I'm going to convince you today of both these properties, but before I want to show you a picture. So how should we think of L0 minimization and L1 minimization? So I have this picture also in the lecture notes. I'll try to reconstruct it somewhat. Right, so the problem is that it's not, the right place to see these things is not in two dimensions. It really is in higher dimensions, but it's very hard to draw in higher dimensions. So I'm sort of stuck drawing in two dimensions, but you can already kind of see it, but you have to try to imagine what would happen in higher dimensions. Okay, so the solution phi, right? So phi z equals y, right, is some kind of, not a subspace, it's a subspace shifted, right, in some affine space. And what you're doing when you're trying to find the L0 norm, right, one way to think about it is that you're trying to find the point that hits the axis, right? Think of this as like, right, growing something like the L0 ball, right? You're trying to find the intersection with the axis, right? And then, you can think of, given the intersection with the axis, you're trying to make it close to the center as possible, say. So you can view this as sort of as the L0 ball. If you think about what the L1 ball means, what I mean by this is all these points have the same of L0 norm equals 1, right? This is what I mean by the ball, right? And I can think of inflating it. Now, the L0 is not really a nice thing to be inflating, right? Because I go straight from 1 to 2. But this is sort of the image to keep in mind. Now, let's look at what the L1 ball does. Right, so what do I mean by the L1 ball? I mean drawing, right, the L1, the space, the vectors in R2 whose L1 norm is 1. Okay? So I realize maybe I should state this like explicitly what L1 norm is. Right, so L1 norm vector, right? I mean, we saw the LP norms before, but maybe I should write it again. Right, I mean just the sum of the absolute values. Okay. So what is the L1 ball? Right, I have my vector E1, or I should say, right, my vector say 0, 1, right, this has L1 norm, 1. I have my vector 1, 0, right, this also has L1 norm, 1, right, there's the 0 minus 1, and this one here. Right, and now what do I want? I want the vectors whose sum of absolute values is still 1, so clearly this is the ball, right? It's this diamond. Right, convince yourself of this. My diamond is quite not so nice at all. Okay, it's think of it as more symmetric than I was able to draw it. Right, so this is the L1 ball. And now what we should think is by when we minimize, right? So if you look at phi z equals y, right? What are we doing when we look at the point in this blue line that has the smallest L1 norm? It's the same thing as thinking of grabbing the L1 ball and inflating it until it touches the blue line, right? And so if I do this, okay, I made this parallel by not being very clever. Let's make this less parallel to be easier to see, right? I can think of inflating this ball, right, until it touches, right? And because the L1 ball has these pointy corners in the axis, the place in which we'll tend to touch first the subspaces will be sparse. Right? So in this case, this point would be the solution, right? The L1, minimum L1 norm solution. Okay, and as you see, it is sparse, right? It is hitting in the axis. And it's because the L1 norm has this property that's sort of pointy around for sparse vectors. Okay, so this was just intuition and pictures. Let's now prove some theorems. So there's two things I want to convince you of, right? So this is the picture to have in mind of why, or a symmetric and nicely drawn version of this picture is the picture to have in mind when you think of why L1 norm promotes sparsity. And it'll promote sparsity here and then in regression and then later on in matrix completion. And now I have to convince you that L1 is easy to solve and that the solution to L1 is meaningful. Okay, so let me first convince you that that L1 is easy to solve. So for this case, I will specifically work with Rn. Right? Because it's a lot easier. It's still easy over the complex numbers to solve, but it's much easier to explain why it's easy to solve over the reals. Okay, so over the reals, it turns out that L1 is equivalent to a linear program. Okay? And so the way to see this is actually quite nice and quite simple, is you create new variables. So you think of W plus. Think of W plus as the positive part, so positive part of X, right, of the variable X. And W minus as the negative part. What I mean by this is, if X is positive, if the entry of xk is positive, then omega k plus is that number, and omega minus k is 0. Okay? If you define these variables, okay, but then we have to optimize over them, then we get a few things, right? So we get that X is equal to X is equal to W plus minus W minus, right? Because it's the positive part minus the negative part. Okay, so, if X is, say, 1 minus 2, right? I think of W plus as being 1, 0, and W minus as being 0, 2, right? So X is equal to W plus minus W minus, and the L1 norm of X is nothing but the sum of the entries of this, right? So it's the sum over K from 1 to N of WK plus WK minus, right? So another way to write this is just one transpose, the whole one's vector, W plus W minus, okay? And so this makes us consider, we can try to write minimum. Okay, I should have used the letter Z. Yeah, let me use it instead the letter Z instead of X, sorry. It's going to be a bit easier too, because that's what we used as a variable. Okay, so minimum of Z, one norm, such that AZ, right, not A, sorry, phi Z equals Y, right? I can now try to write it in this way, in which I minimize, right? What is the norm? Is just 1 transpose W plus W minus, such that, right, what do I have? I have just phi W plus minus W minus is equal to Y, right? And what do I know about W plus W minus? I know 3 things about W plus W minus. They need to be positive, right, because of the way I wrote them. And there's this other thing, which is they can't both be 0. They at least one of them needs to be 0, right? For all k, either WK plus or W minus k is 0, right? If I have the property that these vectors, for every entry, at least one of them is 0, right? And they are both positive, then when I take the difference and I make a vector, they are for sure the positive and the negative part of the vector. Now all of these are linear constraints, right? Everything is linear in W. But this one at red is not. Okay, but I claim that the one in red doesn't. I don't need the one in red. Okay? So I claim that even if I remove the one in red, that this is still equivalent. Okay, so let me give this a name. Let me call this, like LP1. Okay, this is all in the lecture notes as well. right? The one norm version, the linear program for the one norm. Why is this equivalent? Well, the only thing I have to show is that any optimal solution of this will satisfy that for every k, at least one of them will be zero, right? So we're going to prove any optimal, an optimal um, I mean, okay, I don't, right? Yeah, okay. So I just need that there exists an optimal solution, yes. No, I should say any optimal, okay. Any optimal solution to LP1 will satisfy that for all k, we have wk plus equals 0 or wk minus equals 0. Right? If I prove this, let's call this a proposition. If I prove this, then indeed these programs need to be equivalent. Right? Because if I prove that, then we know that they were equivalent if I had the red thing. Right? So maybe let me take this out. It's clear that in this case they are equivalent. I'm just reformulating. If I prove that any optimal solution for the one without the red thing needs to satisfy the red thing, then this linear program is equivalent to L1 minimization. But if you think about it, this is actually quite trivial, right? Because let's suppose, assume that this wasn't the case. Right? Assume that, say, WK plus was bigger or equal than some epsilon, and WK minus was bigger or equal than some epsilon, right? For some epsilon bigger than 0, right? So we're proving now that, right? Then it's very easy to see that you could do a better objective. Just take a new solution, W, plus, I guess there's too many things here. Let's say tilde equals to WK plus minus epsilon, and take WK minus tilde to be WK minus epsilon. I mean, this is a lot of letters and so on, but really the idea is very simple. This is a better solution. So is feasible for LP. Okay, why is it feasible? Because they were bigger than epsilon, so they're still bigger or equal than 0. Because I'm adding in both of them, and the constraint involves the difference, then of course it's still feasible, right? Because they are still non-negative, and the difference is still the same, right? Why they're feasible? They're bigger or equal than 0, bigger or equal than 0, and WK tilde plus minus W tilde minus K is equal to what they were before. So they're definitely feasible, right? And the objective got smaller, right? Because what is this now? 1, 1, right? 1 transpose WK minus plus W, sorry. Right, so W tilde is the same thing for the other, right, for the other variables. Maybe I should make this a bit more precise, right? I mean, I think this is obvious, but okay, let me just, right? So for other j's are just the same thing as like plus or minus for j, not k, right? Then, right, so the difference between the vectors is the same. They're still then negative, so of course this is all satisfied. And if I look at what happened here, right, this is equal to what it was before. So W TW. This is the kind of thing that it's easier for you to just try than maybe to watch me do it, but okay. And like one, right? This is what happened. All the other entries, I'm summing all the entries of this. All the other entries are the same. The entry in K changes, but what I'm reducing is 2 epsilon. So this is equal to this minus 2 epsilon. Right? So it has a better objective. Okay, so If I start with the solution of this LP for which there is a K for which both of them are positive, I can shrink them to zero. Everything is still feasible and I improve the solution. Okay, so basically we prove that this L1 is completely equivalent to this LP1. And as you'll see, or maybe you've seen in a class, linear programming is efficient. So this is efficient to compute, efficient to solve. Okay. We won't talk much about linear programming, but the point is if you were to put this on the computer to solve, this is something that the computer can solve easily. Okay, now about the complex case. So for the complex case, clearly I can talk about the positive and negative part, and the L1 is the L1 norm is a bit more delicate. So you have to, but the point is that it's still convex. Like this objective is still nice and convex, but talking all about convexity is not in the scope of this course, so I won't mention much about it, but the way you prove that it's efficient is not the same way, but it's still efficient. The point, at least for reals, this is a linear program. Okay, so now let's get to the more interesting thing. Okay. And this is the kind of thing that, like, I think if you think about it for 2 minutes, this is obvious that, this is equivalent to this linear program, and seeing all these reductions is maybe more complicated than if you just think about why they can't both be positive at the same time. Okay, so now I'm going to convince you. Now we want to understand when is it that X is the unique solution. Okay, so, let me write this in better terms, so make bigger. Right, so now we're going to answer the second question, right, which is really the interesting question, which is when is X, say S sparse, the unique solution? And now I go back to K being reals or complex, right? So maybe I should make back to R or C. It was just that little part that needed R. Okay, when is X S sparse, the unique solution to L1? Okay, now we know that this is something we can solve. Okay, so now this is the central question that we're going to answer in the last 25 minutes or so. Okay, so we're going to prove, I'm actually going to prove and motivate the definition about the matrix phi at the same time by just trying to answer this question. Okay? And as we answer this question, what you'll see is we'll learn quite a bit about what makes this be the case. So let's say that S, okay, so now let's answer this question, and we're going to prove a theorem as we answer this question, and I'm going to make the theorem very explicit. Okay, so let's say that S is the support of X. Okay, so what do I know? I know that S size, say S, that potentially can be smaller. Okay, this is what I know. I mean, it could potentially be smaller. Sometimes you say S sparse, but it's like, it could be smaller, right? But it's okay. This is not going to be needed for now. Okay. Now suppose, let's suppose that there is a better solution. Suppose, right, that Z different than X is also an optimal solution. Is either, X could be optimal and Z also, but let's say that there's a solution different than X that is a solution to L1, is an optimal solution. Of L1. So what does this mean? This means that, phi Z is equal to I, and it means that the L1 norm of Z is smaller or equal than the L1 norm of X. So we want to rule out we want to rule out the fact that such vectors can exist. Okay, so how do we do this? Let's look at Z minus X. Let's define this vector Z minus X. What do we know about it? What do we know about this vector? We know that, phi of V, right, What is z? Z is v plus x. So phi of v plus x is equal to y, which is the same thing as phi of x. Right? I mean, in other words, right, phi of v is 0. Right? V is in the kernel of phi. Right? Right? If both of them satisfy the measurements, then their difference must be in the kernel. Okay? So we know that. What else do we know? We know also that, right? We know that it must have smaller L1 norm. Okay? But all the L1 norm in, okay, so let me give a notation. So when I grab a vector, say x, and I mean s, I mean the vector x restricted to the entries. This is standard, but to the entries in set S, in S. Right? S is a subset of the possible n entries, and this I mean the restriction of the vector. Right? Okay. So now the L1 norm of, right? So the L1 norm of x is actually, because the big set S is the support of x, it's completely explained by just the norm of the L1 norm of the vector in those entries, right? Because all the others are 0. Right? Okay. But we know also that this must be bigger or equal than the L1 norm of z. So this must be bigger or equal than x plus v. Right? Okay, so far I haven't done much. But now the norm of x plus v, the L1 norm of x plus v, right? If I have an L1 norm of a vector, is the sum of the absolute values of the entries. It is, if I look at a particular subset of the entries, the L1 norm is the L1 norm on that subset of entries plus the L1 norm on the rest of the entries. Right? So now I can write that this is equal to, right, the norm of x plus v in S plus the L1 norm of x plus v outside of S. Right? With the L2 norm, you have to be a bit more careful, right? You have to put a square root and so on, but with the L1 norm, this is perfectly fine. Okay, why did I do this? Because x is 0 in S complement, right? So that part is going to disappear. Okay, so this is equal to. So what do I have? Let's be a bit more careful. So I have, right, say, okay, so we have norm of x plus v in S. So I can write x, s plus v, s, right? Or I can write x plus v in S is of course the same thing. Plus, the right x here has no norm, has no entries in S complement because S is the support of A. So I get just this. Okay. But now now let's think about this for a second before I go and complete the proof, which basically is done almost. But let's think about what we're saying here. So x as supporting S. We're saying that when we add V, the L1 norm reduces, right? It gets smaller. But this part outside of the support of x can only get bigger because it was 0. It's like the minimum possible norm we can get. So this term can only contribute positively. Right? So all the contribution that V is being able to push down the L1 norm of x is happening in this small support. So you have a vector x that's very sparse. Its support is concentrated in very few entries. And this matrix V in the kernel, this vector V in the kernel, is being able to push down all those entries, like, or at least some of those very few entries down, while not pushing up any of the zeros. So somehow it's already saying that V needs to have most of its energy also in S, but not outside of S. Okay? And you know, if the matrix phi is nice, there won't be vectors in the null space that satisfy this. Okay, so now that we got some intuition, let's continue with the proof. So how do I say this? The contribution from this term needs to be positive the contribution from this term can potentially be negative. So let's bound it by just triangle inequality. Okay, so this is big or equal just by triangle inequality, xs, one norm, minus, right? How much the one norm can reduce by adding something can be as at most, right? I mean, this is just triangle inequality, right? Plus, right? So this is triangle inequality. Okay, so what does this tell me? Right now, this term showed up here and showed up here. So it tells me that V is in the kernel of phi, and it must be that V in S, one norm, needs to be bigger or equal than V in S complement. Okay. So the only way that the L1 recovery problem doesn't recover X, the only way that there's a spurious solution is if there exists a vector in the kernel of phi. There is in the L1 norm much more supported in the set S, which is very small, right? Remember, the set S is much, much smaller. We think of this as much smaller than N. So somehow vectors in the kernel need to be very, very spiky, right? In a very small number of entries, they need to have most of its L1 mass, right? And we don't expect this to happen. Okay, so let's give a definition. Let's just make the definition that will make this work. So let's make the definition. We say that the matrix will be nice for this purpose if no vector in the kernel has this property. Okay, so this is like, this now motivates a definition. So definition, right? This is the definition of null space property. Again, it's the following. Phi is said to satisfy the S null space property. Okay, so this is often called SNSP. Okay, if for all V non-zero in the kernel, the null space of phi, like that are not zero, right? I don't care about zero. And all S whose size is S, right? And of course smaller. If it satisfies for all things of size S, will also satisfy for things smaller. We have that L1 norm in S is smaller than norm in S complement. Oi. Okay, so we say that the matrix satisfies the null space property if, for a number S, if all the vectors in null space are sort of evened out. They're not very spiky. There's no set of small coordinates where they have most of their L1 norm, okay, most of their L1 mass. Okay, and so above, what did we prove above? Right, so let me write a theorem of what we proved above. Right, we proved that if phi satisfies, right, this is exactly what we proved above, that if phi satisfies the S null space property, then if phi satisfies that null space property, then for any x s sparse vector, X is the unique solution of L1. Okay, so the L1 minimization really gives us what we want. Now, I left as a challenge to prove the converse, that if L1 recovery works for any S-sparse vector, then it needs to satisfy the null space property. Okay, so sort of you can think of it as homework, prove a converse of this. It's good because you'll see, like you'll get a bit more used to these notions, and it's essentially a very very similar idea, right? If it doesn't satisfy the null space property, you try to find a vector x that's as sparse for which you wouldn't have exact recovery necessarily. Okay? So think about what I mean. I still have to build. I still have to argue that these matrices exist, right? Otherwise, we're not right. I still need to. We still need to show these like these matrices exist. Otherwise, it's all for nothing, right? Right. So we're still going to do that, but think about what we've done. Provided that you're convinced that this matrix exists, which you shouldn't be yet. Then this is saying that this computationally easy problem to solve, this L1 recovery, actually is a way to solve the problem that seemed very difficult of finding the sparsest vector, the sparsest solution to a linear system. And we know that, if we have, provided the matrix has nice spark and so on, it's actually, if I have a sparse vector I want to recover, I can take measurements that potentially are a lot less, like D might be a lot less smaller than N, and I still get exact recovery. I can still recover X from very few measurements. And this can be used for example, MRI, say. Okay, so how are we going to prove this? Okay, so the main theorem we're going to prove is, so we're going to take, theorem. I'll now state it as a theorem and prove it rather than proving it and then stating it as a theorem. So theorem, okay. Let's say phi as unit has phi with unit. It's okay. So let's say, right, so k d by n, and let's make it unit norm vectors with unit norm columns. Okay. Okay, let mu be the worst case coherence. Of phi, right? Recall, mu was the max for I different than j of just phi, the inner products, right? So phi I, phi j. Okay, we have this definition. Okay, if the sparsity is smaller than 1/2 times 1 plus 1 over the worst case coherence, okay, then phi satisfies the null space property. Okay, so if I can design matrices or frames with very small worst case coherence, then I can actually do compressed sensing for very large S, right? The smallest the worst case coherence, the largest S. Particularly if the worst case coherence is 0, and this would be infinity, so I could do it for any, I don't need sparsity, right? Which is clear, right? Because if all the vectors in my columns are orthogonal, then basically I have, right, I don't have any underdeterminist, right? The system is not undetermined. This is just an orthogonal matrix, and I'm just doing a normal linear system, right? So we can assume, if mu is 0, then the problem is trivial. There's no constraint the sparsity, of course, because it's not underdetermined at all. Okay, so let's prove this theorem in the last 6 minutes. It has a nice simple proof. Okay, so if mu is 0, this is easy. It's trivial, right? Because then they all right. All the columns are linear independent. There's sort of nothing to do. So let's focus on mu bigger bigger than 0, right? So that we're not dividing by 0 is a bad idea. So we'll focus. We'll focus on mu bigger than 0. Okay. So now, how do we do this? Okay. Right, because I mean, I should say, right, so maybe I should say another word, right? The kernel of the matrix is empty, right? If mu is 0, there's nothing in the kernel. And so the null space property is about everything in the kernel satisfying something. Of course, if there's nothing there, they satisfy everything, right? It's an empty tautology, right? Okay, so now let's say that I have, okay, let's now focus then on this case, and let's say that I take V to be in the kernel, right? And of course, the kernel should be in an empty, right? Otherwise, again, this is of course, and this is of course trivial. Okay, let's take V in the kernel, and let's take K to be a number from 1 to n. Okay, what do I know? I know that sum for L1 to n, right, to phi L, VL, right, that this is equal to 0, right, by the fact that it's in the kernel. Someone asked a question about, so worst case coherence, okay, let me write this a bit more. Worst case coherence is the worst possible inner product, size of the inner product. So this is equal to the max over I different than J of the worst possible inner product that you can get, phi I and phi J. Okay, so if they're orthogonal, this is 0. If you want to pack more than d vectors in the dimensions, you can't make them orthogonal, so this needs to grow. And next week we're going to understand how much can we make this not grow. Right? So we want to get this to be small. Okay? And so there's a whole area of trying to design these objects with a small worst case coherence. Okay, so now the proof is actually quite simple after we set it up. Okay, so we have this, right, because V is in the kernel. So what does this mean? This means in particular that phi k, Vk, is equal to minus sum over all L different than K of phi L VL. I'm just, right, sending all the others to the other side. Okay. But we know also that, right, phi k, L2 norm, is 1, right, because they were a unit norm. And so what can we do? We can just multiply by phi k star on the other side, right? The transpose, or when they're complex, the transpose conjugate. So Vk is equal to minus some L not k, right? I'll try to do this. Okay, so it goes inside, right, because it's a linear thing. Okay, so far so good. Okay, this is equal to 1 because this is just equal to the norm, right? And so I have, and I have that, then Vk is equal to this, but now I can use, just triangle inequality again, right? So I know that Vk is now smaller or equal than, or I should say is equal, let's start with equal, to, I can take away the minus sum, L different than K, this inner product, right, phi K, phi L, right, I don't need to put the inner product, let's just say this, VL, right? But this is now smaller or equal than if I move the absolute value inside. Right? Okay. But now this is smaller or equal than mu, right? The definition of worst case coherence, right? And so what this means is that this is smaller or equal than sum L on K of mu VL. L not equal to K. Okay, so what do I have really? Let's rewrite this here now. Vk is smaller or equal than the sum L different than K. Let's move the mu outside. This will be nicer. Mu sum L not equal to K of VL star. Okay. But what is this sum? This sum is just, it's almost the L1 norm of V. It's just missing VK. This is just the L1 norm of V minus VK. That's it, right? And so this is equal to mu V1 minus VK. Okay, so what does this mean? Right? This just means that 1 plus mu, okay, norm of vk is smaller or equal than the L1 norm of v. Right? No entry can be too large. Right? No one entry of v can be too large. Right? Because remember, mu is bigger than 0, so I'm saying no one entry of v can be just too large, right? I'm saying that every entry of v needs to be smaller or equal, even when you multiply by something bigger than 1, then the L1 norm of v. Okay? Ah, mu. I'm missing a mu there, of course. Okay. Mu. Okay. But now we're done, right? Because now, take S, a subset of N, with size S, right? So right now we're completely done, right? Because what is Vs? This is equal to the sum K in S of Vk, right? But we know that this is smaller or equal than, right? How many there are? There S times, right, mu over 1 plus mu, right? I'm just grabbing this term, sending it here to divide, right? Times the 1 norm of V. Okay, but what is this? It's equal to S. Right, what do we know about S? S is smaller than 1/2 1 plus 1 over mu, right? So we know that, let me write it here, S is smaller than 1/2 1 plus 1 over mu, right? So, right, this is the same thing as 1 plus mu over mu, right? And so by this fact here, we just have that now this is equal, or smaller even, not just smaller equal, then 1/2 times 1 plus 1 over mu times mu 1 minus mu, all the mu's cancel out, the 1 norm of v. Okay, but now we're done, right? Because the 1 norm of v is equal to the 1 norm of v in S plus the 1 norm of v in S complement, right? So we have that the 1 norm of S is smaller than 1/2 of the L1 norm in S plus 1/2 of the L1 norm in S complement, right? And this is done, right? Because now I can move this subtracting to the other side, take the halves. This means that VS1 is indeed smaller than VS complement 1. And so we're done, right? Because for any V in the, oh, not contradiction, sorry. We're done is in like, yeah, QED. Right? Sorry for taking 3 extra minutes. Now it's done. So if, right, V was in the kernel, we use the worst case coherence to show that V cannot be too spiky. Every single entry of V cannot account for too much of the L1 norm. And because in S, there's very few, there's only S entries, they together cannot count for more than half the norm. Okay, so this was the proof of the theorem. Okay, I'm happy to stick around if there's any questions, but sorry that I already took 4 extra minutes, or 3. Yeah, I'll stick around if there's any questions though.